Well, welcome to the 1.3 pre-class video assignment. In this video, we're going to look at something called direction fields, also known as slope fields. This basically is a method that allows us to visualize or even graph a solution to a differential equation, or basically visualize a family of solutions for a differential equation without actually solving the differential equation. The method here only applies to first order DEs. And again, it is convenient here to consider our first order DE in what we used to call normal form, where it is solved for dy dx here. So if we have a generic DE first order solved for dy dx, then on the other side, we have a function that involves, or an expression involving x's and y's at most, yes. So the idea here is this. If you consider the coordinate plane and pick any point from the coordinate plane, let's call it x0, y0, what we can do is we can take this point and we can insert it into this function f of xy. If we do that and evaluate it, we basically get an expression for dy dx. So we get a value for dy dx, I should say. And again, from Calc 1, we know dy dx is the tangent slope to the curve y. So by doing this, by evaluating f of x0, y0, we are essentially getting an idea of the tangent slope of a solution curve that passes through the point x0, y0. So that is basically a fairly logical thing to do here, not too difficult to do, and basically conceptually just taking some first Calc 1 knowledge there. So to expand on this idea, what we can do is now take a bunch of points throughout the coordinate plane and repeat this computation in many places and compute a bunch of tangent slopes, and then plot what we call a slope indicator for each one. Also known as lineal elements. I think the term slope indicator is a nicer term here. But basically, we plot a little line segment that depicts the slope at each point at a bunch of points in our coordinate plane. So when we're done with all this, what we end up with is a graph called a direction field or a slope field. The only difference between a direction field and a slope field is in a direction field, we have little arrows on the end of our line segments on the end of our slope indicators to indicate a direction of travel. In a slope field, you do not. They would just be little line segments. Practically speaking, there's no real difference. Again, so the concept here is quite easy. The work is quite easy. But this is not very practical by hand because it's just a lot of computations, a lot of tedious, laborious work to plot something. And so this is something that can be done using technology. If you Google slope field calculator in Google, you can probably find online versions of this. It is also something we can do on our on a graphing calculator on the TI-89. So we will talk about that in class, but here we'll just look at it by hand. So here is an actual fairly simple example. Let's consider the first order DE, dy dx equals x plus y. I claim that this guy right here is indeed its direction field. We don't really want to do this direction field by hand. You might see it looks like there's about 20 slope indicators horizontally, about 20 of them vertically. So you'd have to compute and plot 400 slope indicators to fill out a coordinate plane like this. Not much fun. However, given this coordinate plane, we can double check some of these locations and just see that it makes sense, and just see that this is indeed looks like the direction field for this particular first order DE. So to do that, let's take a little look-see here. So our first point here at the point 1, 2, what would be the slope of the tangent of the solution curve? What would be the tangent slope to our solution curve? Well, we take the point 1, 2, we plug it into the f of xy function here. So if you put in do f of 1 comma 2, it's just 1 plus 2 equals 3. So 3 is a fairly steep, positively sloping tangent line. So let's go and take a look here. Let me go see here. If we go to the point 1, 2, this is right here. So hopefully we are satisfied that indeed this little slope indicator there is again, that it's plausibly indicating a slope of 3. Here's another one. What about at 0, 1? Plugging in 0, 1, we would get a slope of 1. So at 0, 1, we should have a slope of 1. So 0, 1 would be right here. And if we look at this little slope indicator there, hopefully that is convincing that that is plausibly a slope of 1. Lastly, what about at negative 4, 4? Clearly, if we plug that in, we get negative 4 plus 4 is 0. So if we go to negative 4 plus 4, we end up right here, and that is our little slope indicator there. And again, that is looks like a horizontal slope indicator, hence slope of 0. So this all seems to check out. So again, we're not going to spend time filling out coordinate planes like this too much, but there is a little exercise for you to practice this and get a feel for this on My Open Math. So give that a go now. All right, so once we have a direction field plotted, we can do things like, well, you can kind of picture the whole family here, but we can also solve particular initial value problems. So for example, the question here says, on our direction field, sketch the graph of the solution to the initial value problem, y of 0 equals 1. What we're really saying here is the initial value problem is dy dx equals x plus y with the initial condition y of 0 comma 1. Excuse me, that's not right. Y of 0 equals 1. Again, what we understand this to mean is this is an initial point on our graph. This is the coordinate point 0 comma 1. So I can go ahead and graph in the solution for this initial value problem. It is, if we go to the point 0, 1, which is this point here we already started with, I can then start sketching the curve that must pass through this point. So my goal here is to sketch a curve. The idea here is I'm not trying to necessarily join slope indicators together. I am trying to draw a curve that goes with the flow. It goes parallel to all the slope indicators. So that's what it would look like going in a forward direction. We can also picture what it would look like going in reverse. So in reverse would have looked something like this. So this would have been our solution. This is a graph of our solution function to this initial value problem. Let's try the other one real quick. So the other initial value problem, let's pick a different color. The other initial value problem would have been dy dx equals x plus y. And the condition here is y of 2 equals negative 4. So for us, this is an initial point 2 comma negative 4. So if I go and locate the point 2 negative 4, 2 negative 4 looks to be in here somewhere. If I look at that point right there, I can again attempt to sketch in a curve that flows parallel to these slope indicators. And if I work backwards, it would look something like this. So this would be my solution, a graph of my solution to this initial value problem. And again, the general concept here is in this direction field, we actually have a family of solutions here, and that is, in this family of solutions, this plane is chock full of these curves. This plane is chock full of all these curves. We are simply picking out a couple of family members that fit our initial condition description, i.e. pass through a specific the specifically chosen point. In this case, our specifically chosen point was 2, -4. So this was the particular family member we were picking out. So that's the first page of the notes. We will cover the rest of those notes in class together. What remains here for the video is some prerequisite material. So I want to talk about a couple of concepts that we will talk about later in this note packet. We're going to be talking about something called autonomous first order differential equations. And I think this is also an opportunity to approach differential equations graphically. That's why we are doing it in this section. So a first order DE is autonomous if it is of this form. So this is dy dx equals f of y. So the significance here is that f of y is a function of y only, no x's, right? So in general, this function here could be f of x comma y, but when it is an f of y only, that is when we call it autonomous. In this particular situation, and we will talk more about it when we get to there in the notes, but in this particular situation, we can again understand a fair bit about the solution to these DEs without actually solving them. And the method involves finding the zeros of the function f of y and solving inequalities such as these. That is, where is f of y positive, where is f of y negative? So convenient functions for this, and this is really making a sort of book problems out of them. It is convenient if f of y is a polynomial in y. So that is what a lot of these questions will involve. So a little review about some polynomials. Again, a couple of things here. Polynomials can be expressed either factored or expanded. For our purposes in this section, we like them factored, factored form is preferable because in factored form, we can see where the zeros of the function are. So a little reminder here, a zero of a function is a place where the function's output equals 0. So the x value that causes the function to be 0 is called a zero of the function. In a function f of x, a zero of the function corresponds to x-intercepts of the function. In a function f of y, a 0 would correspond to the y-intercept of a function. And it's actually the second case that we will be more interested in. Mathematically, it really doesn't make any difference. Just a quick note on terminology here. There's really very little difference between zeros and intercepts. The only technical difference is that intercepts are typically thought of as being the coordinate point at the intercept, whereas the 0 is just the value on the axis at the intercept. So what we're really talking about here are the zeros. All right, so if we have a polynomial in factored form, we can easily read off what the zeros are. In this case, if we have a factor of y minus a, then if y equals a, this whole function will be 0. If you plug in y equals a, you will get a 0. Hence, y equals a is a 0. And you can see it sitting right here. If y minus a is a factor, then y equals plus a is a 0. Similarly here, y equals b is a 0 and y equals c is a 0. So in factored form, we can read these off rather easily. A little quick note about possible exponents here. Factors may occur more than once. So here I have the factor y minus a occurring m times, y minus b occurs n times, and so on. These are called, the number of times the factor occurs is called the multiplicity of the 0. So here we would have that the 0 y equals a has a multiplicity of m, the 0 y equals b has a multiplicity of n, and so on. So, all right, quick little question here. If you want to just work the little problem, practice on that on my open math here. All right, so what is the significance of multiplicities? Multiplicities tell us a little bit about the behavior of a graph around a zero. It's really as simple as this. If the multiplicity of a zero is an odd number, then the function crosses over the axis at that zero. I like to keep in mind some simple examples. Y equals x cubed, rough graph of it looks something like this. Y equals x cubed has a 0 at x equals 0, and that is a place where the graph crosses over the axis. On the other hand, if the multiplicity of a 0 is even, then the function only touches at that point. So think of it as being like y equals x squared. Y equals x squared has a 0 at 0, but it only touches, the graph of the function only touches the 0 and goes back again. It does not cross over. So here's another little exercise. This is not unlike the last exercise, but in reverse. So you should be able to, given certain information about zeros, you should be able to construct a polynomial. Okay, so last little topic here before we move on. Again, ultimately, what we're interested in is solving inequalities like f of y positive, where is f of y negative? So let's take a brief look on the method for something like that. So for example, let's say we were to solve the inequality x minus 2 times x plus 3 squared. Let's say we were solving, where is x minus 2 times x plus 3 squared greater than 0? How do we go about solving this? So this is something you would have seen in algebra. However, the method is often something that escapes people. It's not hard, it's just more of a visual graphical method, not something we solve algebraically. So we would do the following. The first thing you do is we're interested in when this polynomial is positive. The first thing we do is figure out where its zeros are. That is, we solve the equation x minus 2 times x plus 3 equals 0. So we can see fairly easily here that we have the following zeros. They are zeros at x equals 2 and at x equals negative 3. These would be our zeros here. So once we have those zeros, if you remember from algebra, you would put them on a number line. So here is, again, in order on a number line. They don't have to be plotted per se, but they do need to be in the correct order. And then what we do is we test. So if minus 3 and 2 are the places where this function is 0, then in between these values, on either side of these values, are the places where it is either above, greater than 0, or below 0. So we test it. So for f of x, we can test some points here. So the idea here is test any point that is less than negative 3. For example, let's test x equals negative 5. If you consider x equals negative 5 and plug it in to an expression like this, if I put in a negative 5 for x, then I have a negative 7 factor here, and I would have a negative 2 squared here. So basically squaring it makes this positive factor, this a negative factor, and then we know a negative times a positive would be a negative. So I now know that on that entire interval from minus infinity to 3, this polynomial is in fact negative, i.e. below the axis. So we just continue testing along the way. So here we might test x equals 0 is the obvious choice here. If you put in x equals 0, we would have x equals 0. This would be a minus 2. This factor is always going to be positive because you're squaring it. So if x equals 0, we got a negative times a positive again. Notice I don't care what the value is here when I'm evaluating the function. I care about the sign only. And again, we can see that that is in fact going to be negative again. Here, just a quick point here is you can see the effect of the multiplicity here. The 0, negative 3 had multiplicity 2. Multiplicity 2 says our graph touches at -3 and does not cross over. Hence, this actually makes sense. I had a graph that I don't know what it really looks like, but it must have come up to the x-axis, touched at 3, and come back down again. That is the only way we have below here, but 0 here, right? It must be this format. All right, last one, we can test another point up here, something like x equals 3. It's kind of your choice, but if we test x equals 3 in our polynomial, if I put a 3 in here, I now get a +1. This is always positive, so now I have positive times a positive, so this would be positive. Hence, the solution to where is our polynomial strictly greater than 0, the answer is we are greater than 0 on this interval over here. So I'm going to color this in I can kind of graph it. This is our solution in purple, this interval. So again, that can be translated into interval notation. This is the interval 2, infinity. This would be the solution here. So give this a go. One last question on my open math to try something like that. And that is it then. So we will finish this packet up in class together, and we will see you there. Thank you.